Well, thank you for coming, everyone. Today, I will be talking about how to write a C++ gadget. And for the first part, we're just gonna create a simple C++ gadget that's going to accumulate a bunch of acquisitions together in a k-space buffer. We will send a custom data type between from this gadget to the next gadget, which will reconstruct an image. So it will be very basic on the MRI side, so we can focus on the C++. So that will be like a live coding exercise. And then in the interest of time, I will present how to write a non-Cartesian gadget, first for gridding and then for sense. But we don't have time to do that as a live coding exercise. So that will just be me going through code. But let's start out. So I'll be doing this with Visual Studio Code. I'm on a Windows platform. So first we connect to WSL and open the online bus. There we go. So a little bit about what I'm using here. So this is Visual Studio Code attached to WSL. So this is an Ubuntu 20 installation, and I have a couple of extensions installed. The C++ one is the main one from Microsoft. The CMake tools, which means CMake just works. Another CMake extension just for auto-completion, and then an XML extension for looking at the config files. If we look at the directory, you can see there's a CMake list. So this is intended as a good starting point for writing your own gadgets or your own toolboxes. But this is not actually inside Gadgetron. This is using Gadgetron as an external library. So you can see we have a project here called Gadgetron Tutorial. We start out by finding Gadgetron. We set the C standard to 17 because otherwise things won't compile. And we add a library, and it's complaining because we have no source files. So let's fix that. So we'll start by making an accumulate gadget. And add that to CMake. And now it's happier. So the first thing we need to do is include some things from Gadgetron, in particular node.h. So node.h includes everything that can sort of be inside a gadget chain, including the channel gadget, which is what we'll be implementing a lot of today. So first, we're going to go using namespace Gadgetron because otherwise we get to write Gadgetron a lot. And it is a nice name, but let's not, spend the entire day doing that. Then we create the accumulate gadget, and we want it to inherit from another gadget, a core channel gadget. So the channel gadget, well, I'll show you what it does, but it needs a type. It needs to know what type of data you want to be receiving, essentially. And for this gadget, we want to be receiving acquisitions. If you cannot read the screen, if the text isn't large enough, now would be an excellent time to tell me. Super quiet.
I've had to do it at original size, and then I'm panning to just the bit you're typing in.
Okay.
So people can do that.
Is this better?
Yes.
Excellent. Sorry. So the first thing our C++ class needs is a constructor. Now we could cheat and just borrow the constructor from the channel gadget, but it's sort of nice to know what you need for a gadget to actually work. So it needs a context. The context includes things like the dataset header and the paths to where Gadgetron is actually running from, that sort of thing. And then it needs some properties, which you just go ahead and hand on to the channel gadget that is the superclass. So far, not a lot going on. And now we get to the beating heart of every gadget, which is the process function. This is where stuff is actually happening. So it takes an input channel, and we need to tell it what type we are receiving through the input channel, in this case, acquisitions. And an output channel, which doesn't need a type because we can send literally anything. And we'll come back to that in a moment. Finally, we need to add override because we're overriding a function on the channel gadget. So far, so good. So what we're trying to do here is set up a case base and fill it with acquisitions. And once the case base buffer is full, we send it on to the next gadget. So first order of business is, how big is the case base supposed to be? So we have a header property. Why are we complaining? Okay. We have a header property. Okay, so this is slightly embarrassing. Apparently I can't do this without the IDE helping me. So what's the problem? We had accumulate gadget, it's there. Everyone's happy. Function. Oh, I am really bad at spelling. Okay. At this point, I will literally have to look at the cheat sheet. Okay, so a header is filled with encoding spaces, and typically we only have one encoding space, so we're just taking the first one. It has sorry, this is we are gonna go do a backup strategy right now. And
could we also enlarge the screen a few more notches as well, David?
Yeah, so what we're going to do is I will I will drop down to a lower resolution, which is hopefully easy to follow. Okay. So this is the same directory, just the folder I did my practice run in this morning where everything was working. We were building stuff. Sorry. We're gonna cheat a little bit in the interest of time and add Gadgetron core so we don't get to write core channel get. Every Syrian. Everybody's happy. Semicolon. And we will just borrow. Okay, now I think we are starting to get back on track. Okay, so I guess what this goes to show is that you should not try to programming C++ without an IDE to help you. So now we're getting a lot of nice help. So I don't have to remember what everything is called. So the header has an encoding, which contains recon space and a matrix size, which we want. But we don't only want a matrix size. We also want the number of channels. And we're going to grab that from acquisition system information. Receiver channels. Now, maybe you're wondering, maybe not, why do we use arrows here and dots up here? Well, acquisition system information is an optional field, so it might be missing. The same goes for receiver channels. Even if you have an acquisition system information, you might not have the receiver channels. But we're gonna go ahead and assume that they're, like the gadget will fail spectacularly if they're not. But for most data sets, that's a reasonable assumption. So finally, we can we have everything we need to assemble some dimensions. We take the matrix size X, Y, and you guessed it, C, and then we have the number of channels. Okay, so that was a lot of preliminary exercises. Now we want to actually start grabbing things from the input channel. So the input channel and the output channel, they're very similar to the connection that you saw for Python and MATLAB. Just rather than having one, we have it separated into input and output. So I know that An acquisition consists of an acquisition header, consists of some data and a trajectory, but we're writing a Cartesian gadget, so there is no trajectory. This will just be none. And then we can loop through the acquisitions like this. Okay. Now, oh, we forgot something. We forgot the most important bit. We spent a lot of time creating these case-based dimensions, and then we completely failed to use them. So the HOND array that we are instantiating here, that's like the basic array type in Gadgetron. It's like the ND array in Python, or like the matrix in MATLAB. It's a multidimensional array. In this case, we're making one filled with complex floats, and we want it to have case-based dimensions. And let's get rid of that. So if we were in MATLAB, we would probably be writing something like right. That's how, so the IDX is from the header. So that's how that would work. Well, in Gadgetron, we can do something very similar. We need to add this incantation, and now Gadgetron supports slicing. So we are just assigning the data array, which has dimensions, case-based points, channels, and we want those to go here and here in the combined case base, depending on the ID of the encode step 1 and encode step 2. The next thing we want is we want to save the headers. We're going to need them later when we're doing reconstruction. So let's make a list to put those in. Finally, we need to figure out, are we done? Are we ready to send this case-based buffer on to the next gadget? So we will ask the header nicely if it has a specific flag set. So this is a little different from how we normally trigger with the bucket to buffer and accumulate trigger gadget. So typically they would they trigger when the IDX changes. We're not going to do that. We're going to instead look at the flags in the acquisition header. And in particular, we want to look at the last in slice here. We know it's done. We're ready to send the data on. But what do we want to send on? Well, I prepared in the best TV chef manner. I prepared a little structure here, which includes an HOND array, data, and a vector of headers. So we could put anything in here. Like you could put functions, you could put anything that can be copied, really, that can be sent from one gadget to the next. But we're going to use this acquisition buffer. So the way we send things on is we have the output channel and we just push things onto the output channel. We make an acquisition buffer, and it the K-space, and the header. Let's call that headers to actually tell what's in it. And this move thing here, if you're not familiar with C++, what it does is it takes the data inside K-space and moves it into the acquisition buffer. That way we avoid having to copy anything. Now we need to reset. We need to reset the K-space buffer. Just gonna initialize it again with the headers. There's a nice Boolean method and standard vector, and we are almost done. Okay, so now we made a gadget. We are lacking one important thing, which is this incantation at the end. So you will see a line like this line or something very close to it in every single gadget. And essentially what it does is it creates a hook that allows us to load this gadget from the DLL or SO file when we are running Gadgetron. So we can go ahead and build to make sure that everybody's nice and happy. Yeah, that was fortunate. And we can make our next gadget. I'm gonna call that FT Recon. It's not gonna be super fancy. We're gonna start with a lot of the same stuff we had in the other gadget. And let's go ahead and add that to the CMake file. So we can get some help from the editor. So this is, we're gonna make a new class, FT-Recon. It's also gonna be a channel gadget, but this time it's gonna take an acquisition buffer. Our acquisition buffer that we declared right here. We are gonna have a constructor, but we're just gonna borrow the constructor from channel gadget. And we're gonna have process, input channel, as an acquisition buffer, and we're gonna have output channel. And we don't really need to do any pre-processing here, so we just get right into it. Now, our acquisition buffer consisted of some data and some headers, so we can unpack those in the for loop. Like we don't have to do this at all. It's just here for convenience. You could also just have, so this line could be acquisition buffer instead, if you prefer a little more old school C++. Data and headers. Now, this gadget is just going to work for fully sampled MRI. So what do we need? We need a Fourier transform. So let's grab that in Gadgetron. And we're going to make a new variable, do an inverse FFT on data. That was easy. An isomorph image consists of two parts. We have the data and we need an image header. So let's make that. But we would like to not have to write that image header by hand. And instead, we can just use this image header from acquisition method, which is why we needed the headers. Actually, we only needed just a single header. And I'm just going to use the first. Then we need the header for the entire data set, which is a variable on the channel gadget. And we need the image data so it can, so it'll know about the dimensions of the image. Wait, we're missing something. This is not an image. This is just an FFT of the individual coils. That will not do. We want a coil map. So we can combine these images. Like we could do sum of squares, but that would be too easy and not very nice. So we're gonna do a coil map estimation. We're gonna use coil map inati, which is using the inati algorithm for generating coil map. And then we're gonna do a coil combination with the image data and the coil map. And it wants to know what dimension we have the coils in. We have in dimension number 3. Okay, well, let's push some things. We're gonna move them as well because we don't need them anymore. We move the image header and we move the image data. And we are good to go. We need 2 more things, a colon here because of C++, and a secret gadget export command. Okay, we are ready to compile. So you can actually see what commands it's running. It's just running the build command of CMake. And now it is time to actually look at some images, see what's actually going on. I need to move these terminals a little bit because of our earlier problem. So inside the build directory, you can see we have our libgadgetron tutorial that matches with the library we made here, Gadgetron tutorial. Excellent. And we want Gadgetron to be able to find that. Now, we could do that in a number of different ways. You could modify the LD library path. We could install this SO file inside our lib directory where Gadgetron is installed. But right now we're doing development. We don't want to bother with all that. So we're just going to start Gadgetron right here next to the SO file. And then let's see. Oh, right. Last thing, we have an XML file, which includes an acquisition reader. I've added a noise adjust and remove oversampling gadget. And then we have an accumulate gadget, which we made, and FFT recon gadget. So actually the FFT recon gadget creates a complex image. They're kind of hard to look at. So we add an extract gadget to create a magnitude image. And then finally, we have an image writer. So we get the image back. So let's see what we can do. We're gonna run the client. Gonna use the simple GRE dataset and our file here. Okay, ran. We have some output. I need to do some magic for ISMRD view to work. And we have images. Hooray. And you can see it's reconstruct all 10 of them. So this is the same data set that Christopher was showing a week ago. And everything's working. So now would be an excellent time for questions, if there are any, before we go on to the non-Cartesian. No questions?
I think there was some question, David. How did you set the auto completion? But it's
how I fixed the auto completion. I cheated. So I am quite unsure why it didn't just work. So this is the exact same folder that's in the online class. This is just located somewhere else, and I don't know why. So it couldn't find ISMRD. We can try and go back and fix that. I don't know why this should be required, but and did that fix anything? Cannot open source file. So the short answer is I don't know why the autocompletion isn't working. I can find out later, but I think right now it's gonna take me too long to figure out. I am sorry. Were there any other questions?
Slice, like in MATLAB.
Sorry?
Can you hear me?
Yeah, yeah.
When you enabled slice,
Yes.
so slice is now a reserved word that lives
Slice.
in Gadgetron indexing.
Yes, like, so what you could do, you could also do indexing slice instead. So that would also work. I just do it the other way because this is quite long.
Thanks.
So the slicing works, like it is a limited version of the slicing you have in Python and MATLAB. We can only do slicing like this. We can't do, you know, from some point to another point, that sort of slicing.
And does slicing work in any dimension or just the first and last?
It works in any dimension you want. Like, so it's completely like in the colon in MATLAB or in Python. So we could have like this. Like that's not going to work because the dimensions don't match. But besides that, that's the theory.
Okay, And so this is making a standalone gadget library that gets loaded into the Gadgetron. Is this where you recommend starting rather than trying to put things into the main Gadgetron project?
Indeed. I think this is much nicer. I think there is the temptation when, if you're just modifying Gadgetron, it's very easy to just take an existing gadget and change that one little thing you don't like about it. Maybe like change the data it outputs a little bit, but now suddenly your gadget is no longer compatible with the rest of the world. You can't share it ever because it would break other people's code. So I think having it separate is cleaner, and then you can bring it back into Gadgetron. Everything you need, everything that's available inside Gadgetron should be available outside. If it isn't, it's a bug. So the only time where you need to write code in Gadgetron itself is if you want to add things to like the core of Gadgetron. If you want to add something completely new to the XML, say you wanted to be able to specify I want to run all of this in Azure, and you want to do that directly in the chain. Things like that you would probably need to modify in Gadgetron. But everything else, just writing gadgets and toolboxes, you can do outside.
Thanks.
And it also means that what you're getting is stuff where we guarantee we will not break your code. That's also a bug if we break your code. Sometimes we will deprecate things, but we will give you ample warning, like literally years of warning before we remove anything for good.
We have a question from Sue, how to add the custom-built gadgets, the library files, into the Gadgetron compiled library. I think that's within your CMake lists.
Yes. So what I'm doing right now is I'm not actually installing anything. I would need to add something like this. Hang on. I don't actually remember this. I'm just gonna go and cheat and have a look at how we're doing it inside Gadgetron. Yes, this is cheating, but I don't remember CMake that well. It is mostly copy paste. There we go. So but all Gadgetron needs to find this is that it needs to be somehow on the library path. Like you need to be able to link against this. So you can either do that by adding it, hard coding it into to where Gadgetron is already storing its gadgets, but you can have it elsewhere. In this case, I would typically install to that local lib instead. So you don't need to, so you can run things without sudo. I hope that answered your question.
And I'll just read the most recent question. Why didn't you name the main header file the same as the library?
There is no main header file. Like there, so typically in Gadgetron, you would have a CPP file and a header file, but you don't have to. The only thing you have to is this Gadgetron gadget export. So I would always recommend naming the file the same as the class, but again, you don't have to, no one's forcing you. So I'm just stuffing all of these gadgets into the library. There is no central header file at all that tells me what's in this library.
Great, thank you.
Okay. So now we're gonna go on to non-Cartesian. So non-Cartesian is a mess. Like Cartesian data, it fits nicely in a nice Cartesian K-space. It's easy to deal with. Cartesian data, like they just get K-space from all over the place. So we need to deal with that. That means the accumulate gadget we just made, it wouldn't actually work because this K-space here, like it doesn't fit, say, a spiral. At least it doesn't fit it very efficiently. So I made a spiral accumulate gadget. So a lot of things are going on, but let's take them from the top. The reason this is a spiral accumulate gadget is when we receive acquisitions, even though they could have a trajectory, they typically don't, even if they are non-Cartesian. Most scanners simply don't append them, but sometimes, typically they will tell you in the header what sort of trajectory it is. So we need to calculate the trajectories. We need to calculate the density compensation. We want to append that to the acquisition, and we want to send that on in one package that's easy to reconstruct. So Gadgetron has this trajectory parameters, and that is a variable here on our gadget, spiral trajectory parameters, and that can calculate spiral parameters like the trajectory. We initialize that here in the constructor. It needs like our header, the ISMRD header, and it needs another thing. It needs a single acquisition header, so it knows how many points are in our spirals, because that is not defined in the MRD global header. So that means we want to grab just a single header, a single acquisition, before we start doing any serious processing. And we can do that. We don't have to use this for loop to get things out of the input channel. We can call pop instead. Gives us the acquisition header, data, and the unused directory. Then we can call calculate trajectories and weight with the acquisition header, and it will give us an HON array of trajectories and an HO array of density compensation. But it won't give us the trajectories and density compensation for the entire, for this specific acquisition. It'll give us for the entire acquisition set. So this is a rather large array, and we need to go and grab the specific trajectory. So here we have a vector of HOND arrays. So the individual acquisition, the individual spirals are stored, one in each HOND array, and we initialize that with the data we got from the first acquisition. Then we have another standard vector of the acquisition headers. A third one, again an HOND array, this time a float D2, so a 2D vector for the two-dimensional trajectory points. And we initialize that. Again, we're using the slicing here on the trajectory array, and we use the K-space encode step 1 index of the header to grab the correct trajectory, and we do the same for the density compensation weights. So a little involved, but non-Cartesian pretty much always is. Then we go back to our nice for loop. Here we're just adding the data and their headers. Again, we are grabbing the correct trajectory for this specific header, the correct density compensation, and again, we're looking for the last in slice flag. But we don't want a standard vector of HOND arrays. That's like a list of matrices. So we call concat, which essentially concatenates all the acquisitions, individual acquisitions along a new dimension. Then, so the acquisitions are stored k-space points and then channels. And now we added a new dimension, which was the individual acquisitions. And we would like the channels to be last. So we permute in order to move the channels to the last dimension. And we reshape because we want to combine the first two dimensions. So now we have one array that's containing all the spiral k-space along the first dimension, and then the individual coils along the second one. For the density compensation, again, we do much the same thing. We call concat to create one combined array. We call reshape, or I should mention the -1 means that it should just grab, like you can have 1 - 1 in reshape and it will infer the dimension from that. So if you just have -1 here, you're making a one-dimensional array. And we're pushing that into a spiral buffer, which I'll come back to, moving things onto there. And then we're clearing all the standard vectors. And that brings us to, let's have a quick look at the spiral buffer. It's pretty simple. Has the data, has the directory, the density compensation weights, and the headers. So let's look at the gridding gadget, which is pretty simple. So it has, first we need a matrix size because we don't have, in the Cartesian case, we could just infer what the image size was from the k-space size itself. We can't do that in non-Cartesian, so we need to grab it from the header. We loop through our buffers. We create so this NFFT plan is a non-uniform Fourier transform plan. It's working on floating points. It's in 2 dimensions. We tell it the 2-dimensional size, matrix X and Y. And then it needs an oversampling factor. 1.5 works pretty well. It needs a convolution size, 5.5. Again, if you don't give these parameters, it'll just use the defaults. And finally, we need to give it the trajectories, and it will pre-process. So this pre-process essentially creates a giant sparse matrix for doing the NFFT. And this is typically the most costly step of the gridding. Like, it takes maybe 5 times as long as any other step. So if you can reuse the trajectory, if you're resampling the same trajectories, then that could save you a lot of time. We're not, so we can't do that. We have to create a new one for every set. We make an image, essentially a place to store the output, and we do call compute. So it takes the data, takes the image, the density compensation weights, and we tell it what sort of NFFT we want. We want a backwards, so an inverse NFFT, and we want it non-Cartesian to Cartesian. So that's the basic image reconstruction. We reshape the image. We add this 1 dimension, so it's on the format of the ISMRD. Like ISMRD wants X, Y, Z channels. Then we can do the coil map, the coil combine, the image header exactly as before, and we have a push the image along. So if we look at the spiral recon here, you can see we have the accumulate gadget, the non-Cartesian gridding, and extract. So let us run that. We need to add it. Spiral. So for my day-to-day work, I would typically be using C-Lion rather than Visual Studio Code, but C-Lion is a pay-to-play sort of thing. So I wanted to use this to sort of give you a good option if you can't get C-Lion. I do believe they have free academic licenses. So, and one of the things C-Lion does is it autocompletes a lot better in CMake. So let's add non-Cartesian gridding. Okay, we're good to go. Let's compile some stuff. We're building, it's fine. Let's remove old output. So in case you're wondering, we don't need to restart Gadgetron. Like it will reload the library every time anyway. So nothing to worry about there. We're grabbing the first file here and symbol, oh, not a symbol recon, but a spiral recon. And it will take a little bit of time. This is a sort of large data set. It's like 460 megabytes, but still not too shabby. Let's have a look. Oh, it's a phantom. Hooray! And you can see, so we're doing gridding. It is a little bit blurry, as gridding often is, but still pretty damn decent, if I say so. But we're not satisfied with gridding. Gridding is boring, and sense is not that much slower, truth be told. So I also made a sense gadget. The flow is much the same. The one difference is we need some coil sensitivity maps. So I created a function that actually what this does is just the gridding from the other gadget, but just returns the coil map at the end because, well, we need the coil sensitivities to do sense, and no one was nice enough to send them to us. Due to sort of the linear equations in sense, we need to take the square root of the density compensation weights and apply those to the data. Then we make a non-Cartesian sense operator, which is also a part of the demo. You can see it's down here. And it needs the image dimensions, it needs the dimensions of the data, it needs the coil sensitivity maps, the density compensation weights, and the trajectory. Then we need, so the non-Cartesian sense operator, it's like a linear operator. Think of it as a sparse matrix. It's not, but you could think of it that way. Then we need a solver for a linear system. In this case, we are going to use a CD solver, so conjugate gradient solver. We add the Cartesian sense operator as the encoding, and then we solve and get back our image. So one thing to note here is that our image dimensions are different. So this is just a 3-dimensional image. There are no coils because sense has like built-in coil combination. We get our image header as before, and we are good to go. And I'm almost out of time. So We just add the sense here. It's built. Brilliant. We need to shut down the viewer. And then we do the sense reconstruction. It takes a little bit longer, but not too bad because it only needs to do the pre-processing once and not in every iteration. He says, and then he has to wait. Oh, it's done. So we can open the data. You can see we have the old image here and the new image, and they look completely the same. Yeah, maybe the sense one is a little bit sharper. Well, this is a fully sampled data set, so you wouldn't expect the difference to be enormous, but that's how you would do it. And that is me almost out of time. I'm gonna go just a couple minutes over, because finally I wanted to talk a little bit about C++, about where do I go if I want to learn more about C++ in general. And A Tour of C++ is a very good book for learning C++. Kate Gregory has some excellent talks both on YouTube, but she also has an online course which is free. She did that together with Microsoft. Kevlin Henney also has some excellent talks on YouTube. So I think those are great places to start. And with that, thank you.
Thanks a lot, David. That was a great talk. Do we do some question or we move to the next speaker? Maybe we can stay in time. I don't know. What do you prefer, David?
I am fine with either. Like I can go and answer questions during the next talk, or we can take the questions here.
Maybe just one. There was a question about the implementation of the non-Cartesian FFT.
Mm-hmm.
The question was, is it a greeting followed by IFFT? But I don't.
Yeah. That I'm not entirely sure what you mean by that. But so what's it's a gridding, a convolution, an inverse FFT, and like a deconvolution, a deapodization at the end. So that's the basic algorithm. There is a GPU version, which is, well, it's a lot faster, even though the CPU version is fairly snappy as far as these things go.
And okay, and there was another question that is easy to answer. Is there a way to save the pre-processed information between runs? With the class GT?
No, there isn't anything built in. Like it could definitely be done, but right now we don't have that feature. Yeah.
There was a question: is there a methods for translating from standard C++ types in and out of HOND?
So could you repeat that?
Methods for converting from standard C++ types into and out from HOND.
Well, HOND is a standard C++ type. It's not a standard. It's not like a standard vector. You can copy everything from an HOND array into a standard vector by just calling standard copy. So HOND array is a valid standard container. However, the standard doesn't come with a multidimensional array. Like there just isn't one. So there is nothing to translate to, essentially.
And CUND is presumably the graphical.
Yes, that is the CUDA version, the GPU version of the same concept, but it doesn't support slicing.
Okay, maybe in the QA session we can spend 3 minutes where you show how to allocate a multidimensional matrix using the AND array. So just using the create operator, or if you can prepare just.
Well, so you should not use the create operator ever. If it doesn't have like a deprecated flag on it, it will. So in the code I showed today, I'm creating about a dozen HUND arrays, but I would be happy to show it in a more explicit fashion.
Okay. Yes, exactly. Like without any other material from the gadget.
Right.